To, well, one of the most mind-bending paradoxes at the heart of quantum mechanics. Just imagine two tiny particles, right? Maybe two photons, born from the same event, incredible close together. Now fast forward. They could be separated by billions of light years. Yet if you measure something on one
Well,
particle,
you instantly know the corresponding property of the
exactly, it's the infamous spooky action at a distance.
the thing that even Albert Einstein wrestled with, yeah.
Mm.
It really forces us, as Schrödinger said, to completely depart from classical ways of thinking.
Mm-hmm.
So this deep dive is all about tackling that central tension. We're going to trace the complete life cycle of an entangled state, from its local birth
Okay.
and its eventual demise, but also its startling, distance-defying existence in between.
Right. So the initial question we're trying to unpack is this. Does how close two quantum systems are, does that spatial proximity dictate the extent of their entanglement?
It seems intuitive, doesn't it? Proximity leads to interaction, which leads to entanglement.
Yeah.
And we'll find the causal chain is, well, it's fundamentally correct for creating entanglement.
But only part of the story.
Exactly. It's only part of the story when you look at the whole phenomena. Get ready for some serious aha moments that will probably challenge your everyday intuition about reality.
Okay, let's dive in. To really appreciate this quantum weirdness, maybe we should first get clear on what it isn't compared to correlations we see every day.
Good idea. That's the perfect starting point. The key is distinguishing quantum entanglement from, familiar classical correlations. Think about Bertelmann's mismatched socks, the classic example.
I think I remember this one.
Right, you have a pair, one blue, one red. You put them in separate boxes, send them off. If you open one box and see a blue sock,
You instantly know the other one is red.
instantly. But that's a classical correlation. It's based on pre-existing information. The socks were always blue and red.
Ah, so it's just about discovering what was already fixed.
Precisely. We just didn't know which was which until we looked. That's the first big distinction. Classical correlations come from shared information that already exists, or maybe a common cause.
Okay.
Quantum entanglement, though, it stems from a shared non-separable quantum state. The individual properties, they aren't definite until you actually measure them.
That's fundamentally different.
And critically, classical correlations obey what we call local realism, and they're constrained by Bell's inequalities. Quantum entanglement, amazingly, violates those inequalities.
It breaks the classical rule.
It smashes them, yeah. It operates under completely different principles.
And what about the information itself? You mentioned knowing the whole versus the parts.
That's another profound difference. Classically, if you know everything about the whole system, the pair of socks, you know everything about each part, each sock.
Makes it.
But with quantum entanglement, you can have maximal knowledge of the whole system, say, a pure entangled state, and yet not have maximal knowledge of its individual parts. The subsystems, the individual particles, they're in what we call mixed states. Their properties are inherently uncertain.
Wow. Okay, so you know the pair perfectly, but the individuals are fuzzy until measured.
Exactly. And that measurement itself is different too.
How so?
Classically, measurement just reveals what was already there. You look at the sock, you find out its color.
Right.
In the quantum world, measurement often creates the definite property that wasn't there before. It forces an outcome from a range of possibilities, collapsing the wave function, as we say.
Okay, that distinction reveal versus create, that really sets the stage. How does the math even handle this?
Well, the paradox of entanglement isn't some weird add-on. It's baked right into the mathematical framework of quantum theory. The language itself shows this duality of local cause and non-local effect. In quantum mechanics, a system state is represented as a vector in something called a Hilbert space.
Okay, like a mathematical space for possibilities.
Sort of, yeah. Think of it as a very rich, high-dimensional landscape where all possible states can live.
So for two particles, say our two photons, do we just add their Hilbert spaces?
No, not just add. That's key. For a composite system, like two photons A and B, their combined space is formed by something called a tensor product. It's written HA-HB.
Tensor product? Sounds complicated.
It allows for much richer combinations than just adding. It's this structure that lets us describe states that cannot be broken down into independent parts.
You mean separable versus entangled states?
Exactly. A separable state is simple, like HS bis. Each particle has its own definite state. But an entangled state, like a Bell state, can't be factored like that. Take HA plus HS, H is 2.
Yeah.
Neither particle A nor B is definitely 0 or 1. Their fates are intertwined in one unified wave function describing the whole system.
So the math inherently links them, even if they fly apart. How does the state change over time?
That's covered by the Schrödinger equation and an operator called the Hamiltonian, often just H. Think of the Hamiltonian as the system's energy operator, or the engine driving its evolution.
Right.
For interacting particles A and B, the total Hamiltonian includes parts for A alone, B alone, and crucially an interaction part, H equals HA plus HB plus hint.
Hint. That's the interaction Hamiltonian.
Yes, and this is the term that couples them, that creates the entanglement. Without hint, if they start separate, they stay separate.
And you're saying this interaction term, hint, it's fundamentally local?
Yes, that's the critical point. The
Okay.
fundamental forces described by our best theories, like quantum field theory, have Hamiltonians that act locally. Interactions happen at a point or in a very small neighborhood. They don't just reach out across space instantly.
Okay, so the engine driving the change, the interaction, is local, but the state it creates can have these non-local correlations. That's the tension.
Precisely.
So if the state is entangled, how do we describe just one particle, say particle A, mathematically, if it doesn't have its own independent state?
That's where the density matrix comes in. It's a more general way to describe a quantum state, especially useful for parts of larger systems or systems in probabilistic mixtures.
Okay.
If we have the density matrix for the whole entangled pair AB, let's call it AB, we can find the state of just A by doing a mathematical operation called the partial trace over B. So OA equals TRB-AB.
And what does OA tell us?
This is the key indicator. If the original state AB was separable, then OA will represent a pure state mix. Particle A is definite on its own. But if OB was entangled, then OA turns out to be a mixed state.
Mixed meaning uncertain.
Exactly. I mean, particle A, viewed on its own, is in a probabilistic state. It lacks definite properties. That mixedness is a direct measure of how much information isn't in particle A itself, but is stored in the correlations it shares with B.
So maximum knowledge of the whole doesn't mean maximum knowledge of the parts. The information is in the connection.
You got it. That's a hallmark of entanglement, captured right there in the math. The framework allows this holistic, non-local connection, even though the processes driving change are local.
Which brings us right back to that core puzzle and how these things are actually made. The theory makes room for it, but how do labs actually create these spooky connections? What does it take to get two particles entangled?
Well, in labs today, generating entangled states is pretty routine, actually. And all these methods confirm a unifying principle. Entanglement is born from physical interaction.
And interaction requires
Proximity.
Yep.
Spatial proximity. The particles need to be co-located, or at least their wave functions need to overlap significantly. Interactions in quantum field theory, our fundamental description, are local. There's no action at a distance allowed for creating the entanglement.
Okay, but what about things like entanglement swapping? I've heard of that, where particles get entangled without ever, meeting. Doesn't that seem non-local?
That's a great question, and it looks non-local at first glance, but it actually reinforces the principle.
How so?
Entanglement swapping relies on a sequence of local events. Let's say you start with two separate entangled pairs, pair 1 to 2 and pair 3, 4. To entangle particle 1 with particle 4, who have never met, you take their original partners, particles 2 and 3, and bring them together.
Ah, so 2 and 3 need proximity.
Exactly. You perform a specific joint measurement on particles 2 and 3 locally. That local measurement action then projects particles 1 and 4 into an entangled state. Proximity was still required, just between particles 2 and 3.
Fascinating. So local steps underlie even that. What's a really common way labs generate entanglement directly?
One of the workhorses is spontaneous parametric down conversion, or SPDC.
SPDC.
So you take a high-energy pump photon, usually from a laser, and you shoot it into a special nonlinear optical crystal. BBO is a common type.
Inside the crystal, what happens?
Inside the crystal lattice, that pump photon gets annihilated, it disappears. And in its place, two new lower-energy photons are spontaneously created. We call them the signal and idler photons.
And this whole creation event is localized.
Highly localized, yes. It happens right there within the structure of the crystal, maybe a few millimeters across.
And how does that localized event entangle them? What's the mechanism?
It boils down to conservation laws, physics fundamentals. The conversion process, happening right there inside the crystal, must strictly obey conservation of energy and conservation of momentum.
So the energy of the two new photons adds up to the original pump photon's energy.
Exactly. APTS plus AI. And same for momentum, PP equals APS plus pi. These conservation laws, applied at that specific point of creation, are what forge the entanglement.
Can you give an example, like with polarization?
Sure. In what's called type 2 SPCC, the signal and idler photons are created with orthogonal polarizations. But before you measure, you don't know which is which. The state is a superposition, something like Wernicke's V plus Vry's I.
Meaning if the signal S is horizontal H, the idler I must be vertical V and vice versa.
Correct. They're perfectly anti-correlated.
Okay.
But neither photon has a definite polarization until you measure one, and measuring one instantly tells you the state of the other, no matter how far apart they've traveled since leaving the crystal.
Yeah. So the bond, the entanglement, it's forged right there, locally, due to fundamental laws at the creation point.
Precisely. The crucial action is confined to that tiny crystal volume. After that local creation, the entangled photons just travel outwards, carrying that correlation with them.
And this isn't just SPDC, right? There are other ways.
Oh yes, many. Atomic cascades, where an atom emits two photons in sequence during decay. Their properties are entangled due to angular momentum conservation in the atom, a local event. Quantum dots, too. These are tiny semiconductor crystals, nanoscale, that can emit entangled photon pairs from a localized recombination process.
And you mentioned wave function overlap?
Right, perhaps the most direct form of proximity. If you take two identical particles like electrons and make their wave functions overlap spatially, say at a beam splitter, they can become entangled just due to their indistinguishability. It's literally bringing them close.
Okay, so the experimental picture is really clear. Proximity enables the local interaction that causes entanglement. That initial idea, proximity, interaction, entanglement, that describes the birth process accurately.
It absolutely does. But, and this is the twist, proximity is necessary for creation, but it's not necessary for sustenance. Once made, the connection persists regardless of distance.
Right, so once they're entangled, how do we even talk about the strength or extent of that entanglement? Is it like, a force field that gets weaker as they get farther apart, like a radio signal?
That's a really common way to think about it, but it's actually a misconception. Measures of entanglement aren't functions of distance at all.
They're not.
No, they're fundamentally information-theoretic quantities. They don't measure a physical force that diminishes over space. Instead, they quantify things like the degree of correlation, the amount of shared information, or the inherent uncertainty in the subsystems. They tell us how inseparable the particles are.
Okay, so how do we put a number on that inseparability?
The most fundamental measure, especially for a pure bipartite system, just two parts, A and B, is called the entanglement entropy, usually written SA.
Entropy, like disorder.
Sort of, but here it quantifies the uncertainty or lack of information about one part, say A, when you look at it alone, even if you know everything about the combined system AB. It's calculated from that reduced density matrix we talked about, A.
And what do the values mean?
Well, if the state is separable, meaning no entanglement, the entanglement entropy SA is 0. If it's entangled, SA is greater than 0.
Is there a maximum?
Yes. For maximally entangled states, like a Bell state between two qubits, it reaches a maximum value, which is log base 2 of 2, or simply 1. We sometimes call this one EBIT of entanglement, like one shared bit of quantum information.
Or an EBIT. I like that.
And crucially, SA always equals SB. The entanglement entropy is the same for both subsystems, showing it's a truly shared property, a measure of their mutual interconnectedness.
Okay, so it's a score for the connection, not dependent on distance. Does this score, this entropy, tell us anything about how the entanglement was formed locally?
It does, indirectly, through a really profound result, especially in many body systems, called the area law.
The area law. What's that?
It's the observation that for many quantum ground states, the entanglement entropy between a spatial region A and its surroundings B often scales not with the volume of region A, but with the area of the boundary between A and B.
Only the boundary, not the whole volume. Why?
It's seen as a direct consequence of the locality of interactions. Because the interactions that create entanglement are typically short-ranged, they mostly operate across the boundary between the regions. Entanglement is primarily generated between neighbors.
Wow, so the area law is like a fingerprint of those local interactions left on the global entanglement structure.
That's a perfect way to put it. It connects the local cause to the resulting entanglement pattern in a deep way.
Are there other ways to measure entanglement besides entropy?
Yes, especially for specific systems. For two qubits, for instance, a measure called concurrence is very common. It's a number between 0, no entanglement, and 1, maximal entanglement.
Concurrence. Okay.
It's useful because it's related to how difficult it is to create a given entangled state specifically. The minimum number of simple entangled pairs you'd need, on average, to prepare that state, using only local operations.
Got it. So the extent is a precise information-based property, not a decaying force. And its structure, like the area law shows, reflects the local way it was born.
Exactly.
Okay, so created locally, strength isn't about distance.
hmm
But now we hit the really weird part. The spooky action at a distance that, as you said, bothered Einstein so much.
This is really the core of the quantum mystery, yeah. It goes back to that famous 1935 paper by Einstein, Podolsky, and Rosen, the EPR paper.
Right, EPR.
They weren't actually questioning entanglement itself, but whether quantum mechanics was a complete description of reality.
What was their argument?
They imagined a thought experiment with two entangled particles, set up so they have perfectly correlated positions and perfectly anti-correlated momenta. Then you let them fly far apart. Their argument rested on two seemingly reasonable assumptions. First, the principle of locality, no influence can travel faster than light. What Alice does here can't instantly affect Bob over there.
Seems reasonable.
Second, what they called a criterion of reality. Basically, if you can predict with certainty the value of a physical quantity on Bob's particle without disturbing it in any way, then that quantity must correspond to an element of reality. It must have had that definite value all along.
Okay, predict without disturbing means it was already real, like the socks again.
Exactly their point. So Alice measures particle A's position. Due to the correlation, she instantly knows B's position without touching B. So B's position must be real.
Makes sense under their rules.
Or Alice could choose to measure particle A's momentum. Then she'd instantly know B's momentum. So B's momentum must also be real. Their conclusion. Particle B must have possessed both a definite position and a definite momentum simultaneously all along, independent of Alice's measurement choice.
But that directly contradicts Heisenberg's uncertainty principle. You can't know both position and momentum with perfect accuracy.
Precisely. That was the paradox. EPR concluded that since quantum mechanics couldn't assign definite values to both, it must be an incomplete theory. There must be some underlying hidden variables that determine these properties locally, which quantum mechanics was missing.
Okay, that's a powerful argument. It sounds like just philosophy, though. How did it become testable?
For almost 30 years, it was mostly philosophical. Then, in 1964, John Stuart Bell came along and did something brilliant. He took EPR's ideas about local realism, that combination of locality and pre-existing reality, and turned them into a mathematically testable prediction.
He found a way to test local realism itself.
Yes. He proved that any theory based on local hidden variables must obey certain statistical limits on the correlations you could observe between measurements on the two particles. These limits are now known as Bell inequalities.
So like a speed limit for correlations based on classical ideas.
Kind of, yeah. A common one is the CHSH inequality, which says a certain combination of correlation measurements, let's call it S, must be less than or equal to 2, SCA2. That's the limit for any local realist theory.
Okay, so Bell says local realism means S is 2 or less. What does quantum mechanics predict?
Quantum mechanics predicts that for entangled particles, you can actually get correlations stronger than this limit. For the CHSH inequality, quantum mechanics predicts S can reach up to 2 times the square root of 2, which is about 2.82.
Significantly higher than 2.
Definitely. So Bell's theorem presented this stark choice. Do experiments obey the Bell inequality, SA2, confirming local realism and suggesting QM is incomplete? Or do they violate the Bell inequality, S2, proving quantum mechanics correct and forcing us to abandon local realism?
Wow. Okay, that's a clear experimental question. What did the experiments find?
The verdict has been overwhelming, starting in the 1970s with John Clauser, and then famously in the early 80s with the Lane aspect. Experiments have consistently shown violations of Bell inequalities. The correlations are stronger than local realism allows.
So local realism is wrong.
The evidence points strongly that way. But scientists are cautious, and early experiments had potential loopholes, ways that, hypothetically, local realism could still sneak through and explain the results.
Loopholes? Like what?
Two main ones worried people for a long time. One was the locality loophole, or communication loophole. Maybe the measurement settings chosen at detector A could somehow influence detector B via a conventional signal traveling at or below light speed.
How do they close that?
By using very fast random number generators to choose the measurement settings after the entangled particles had already left the source and were in flight. They made the choice so quickly there wasn't time for any light speed signal to communicate between the detectors. Aspected early versions and later experiments by Gregor Ways and others really nailed this down.
Okay, so no secret light speed messages. What was the other loophole?
That was the detection loophole, or fair sampling loophole. Maybe the detectors weren't perfectly efficient, and they were only detecting a biased subset of particle pairs, specifically the ones that just happened to show strong correlations, while the real distribution obeyed Bell's inequality.
Ah, like only counting the favorable coincidences.
Sort of. This was closed by developing extremely high-efficiency detectors, first with trapped ions and later with photons, ensuring that enough particles were detected that the measured sample was truly representative of the whole.
So they closed both major loopholes.
Eventually, yes. The big breakthrough came in 2015. Three independent research groups, led by Ronald Hansen, Riss Justina, and Seiwunam, working with Christer Shalm, performed experiments that simultaneously closed both the locality and detection loopholes, along with other more subtle ones.
Loophole-free tests.
Loophole-free Bell tests, exactly. The results were definitive violations of Bell inequalities with extremely high statistical significance. Local realism, as defined by Einstein, is experimentally untenable.
And they've tested this over large distances too, right?
Absolutely. The Messias quantum satellite, launched by a Chinese team led by Jianwei Pan, distributed entangled photons between ground stations separated by over 1,200 kilometers and still observed strong Bell violations.
1,200 kilometers.
Wow. They even used it for quantum teleportation over 1,400 kilometers. This proves that the non-local correlation persists over truly astronomical distances.
But it's really important to stress this non-locality, this spooky action. It doesn't allow faster than light communication, right? That would break relativity.
That is absolutely crucial. No FTL communication. While the correlation between measurement outcomes is instantaneous, the outcome of each individual measurement is completely random.
So Alice can't use her measurement to send a message to Bob.
No. She gets a random result. Bob gets a random result. It's only when they later compare their results, using a conventional light-speed limited channel like a phone call or email, that they discover the perfect correlation that violates Bell's inequality. Quantum non-locality and special relativity coexist just fine.
Okay, so the history, the experiments, the loophole closures, the verdict seems unassailable. The quantum world is non-local. These correlations, born locally, truly transcend space.
That's the unavoidable conclusion from decades of rigorous experimental work.
So entanglement is born locally through interaction. It then exists with these non-local correlations indifferent to distance. But it doesn't last forever, does it? It's not an immortal connection.
No, unfortunately not. It's often quite fragile. And just as entanglement is created by controlled local interactions,
It gets destroyed by uncontrolled ones.
exactly. It's ultimately destroyed by uncontrolled local interactions with the surrounding environment. We call this process quantum decoherence.
Decoherence. Right, that's a big problem for quantum computers, isn't it?
It's arguably the biggest challenge, yes, because no quantum system is ever perfectly isolated.
It's always interacting with, what, stray photons? Air molecules?
All the above. Stray photons, electromagnetic fields, vibrations in a crystal lattice, collisions with air molecules, any unwanted interaction with the degrees of freedom in the environment.
And what does that interaction do to the quantum state?
When a quantum system in a delicate superposition state interacts with its environment, the system and the environment become entangled with each other. Think of a single qubit in a state like Anshe plus Flissi. It interacts with its environment initially maybe in state Ehoros. The combined system evolves into something like Anshe plus the RA
Yeah.
so the qubit state gets correlated with different states of the environment.
Yes.
The quantum coherence, the superposition, isn't really destroyed, it's just leaked or spread out into the much larger, much more complex system plus environment state.
And from the outside, looking only at the qubit.
To an observer who only has access to the original qubit, that coherence seems lost. The qubit starts behaving more like a classical probabilistic mixture of 0 yay and 1 yo, rather than a quantum superposition.
Okay, so that's decoherence for a single qubit. How does it affect an entangled pair, especially when they're far apart?
The same basic process degrades the entanglement between two particles, say A and B. When they're separated, each particle interacts with its own local environment. Particle A interacts with environment EA, and particle B interacts with its environment EB.
Ah, so they're not interacting with the same environment necessarily?
Usually not, especially if they're far apart. Particle A starts getting entangled with EA, and particle B starts getting entangled with EB.
And that affects their original entanglement with each other.
It has to, because of a fundamental principle called the monogamy of entanglement.
Homogamy, like it sounds.
Pretty much. A quantum system can only be maximally entangled with one other system at a time. It can share partial entanglement with multiple systems, but it has a limited budget.
So if particle A starts getting entangled with its local environment,
Its original entanglement with particle B must decrease. It's spending its entanglement budget on the environment instead. The same happens for particle B and its environment.
that's really crucial. The loss isn't because A and B are far apart, but because each one is locally interacting and becoming entangled with its own surroundings.
Exactly. The global property of entanglement between A and B is eroded by the accumulation of these separate local information leaks into the environment at each particle's location.
So the destruction is also a local process happening independently at A and B.
Yes. The rate of decay depends on the specific type of local environmental interaction, things like amplitude damping, phase damping, etc. And sometimes this decay can be quite dramatic. There's a phenomenon called entanglement sudden death, or ESD.
Sudden death. That sounds bad.
It is for the entanglement. Unlike the coherence of a single qubit, which might decay exponentially towards zero, the entanglement between two qubits can sometimes vanish, completely hit exactly zero in a finite amount of time. It abruptly becomes a purely separable state.
Wow. Not just fade away, but just stop.
Right. It really highlights how fragile this quantum correlation can be in the face of environmental noise.
This really brings the whole story full circle, doesn't it? The role of proximity seems almost symmetrical.
It is, in a way. Controlled proximity enables the local interactions that create entanglement.
Yeah.
And uncontrolled proximity to the environment enables the local interactions that destroy it.
So let's synthesize this. We started asking if proximity dictates the extent of entanglement. And the answer is clearly much more nuanced.
We've definitely confirmed that the causal chain proximity interaction entanglement is correct, but it's really only the story for the creation and, as we just discussed, the destruction phases.
So local cause for the beginning and the end. But what about the middle? The existence phase.
That's where the crucial distinction lies.
Yeah.
Once that initial proximate interaction has occurred and the entangled state is created,
Yes.
the resulting quantum correlation, the spooty connection itself, is entirely independent of the distance separating the components.
That's the non-local part confirmed by Bell's theorem and all those experiments.
Exactly. The loophole-free tests, the satellite experiments over 1,200 kilometers, they prove that these correlations are stronger than any local realist theory could possibly explain. It's a fundamentally non-local effect stemming from a local cause.
So maybe we can outline a refined model of entanglement's life cycle in 3 stages.
I think we can. Stage 1, creation. This is local. Two systems come close. They interact via a local Hamiltonian term, hint, and they evolve from being separate to being entangled. The amount of entanglement generated is set right here by this local event.
Okay, local birth. Stage 2.
Stage 2, existence. This is the non-local phase. The entangled systems can separate, even to vast distances. The non-local correlations persist instantly across that distance. They are independent of separation. Proximity is irrelevant here. Measurement outcomes are correlated in that spooky way that violates Bell inequalities.
Non-local life. And stage 3.
Stage 3, destruction. Symmetrically, this is local again. Each particle interacts locally with its own environment. Because of entanglement monogamy, these uncontrolled local interactions gradually degrade and can eventually destroy the original entanglement between the two particles. That's decoherence.
Local death. Creation local, existence non-local.
Destruction local.
That captures the essence of it. The truly profound, almost paradoxical nature of entanglement lies right there in that duality. It's a phenomenon born from local physics that then manifests as a correlation completely unbound by our usual notions of space, representing one of the deepest and most challenging departures of the quantum world from our everyday classical intuition.